This is a training on NUCAPS soundings that are now available in AWIPS. This training will explain how NUCAPS soundings are created, how to find them in AWIPS and use them, and how to modify them. NUCAPS is the NOAA-unique Combined Atmospheric Processing System. For Suomi-NPP or JPSS, it combines information from CRIS, an infrared sounder, and ATMS, a microwave sounder. From MEDOP-A and MEDOP-B, it combines information from IASI, which is the infrared sounder, and AWIPS-II or MHS microwave sounders. Equatorial crossing times for the different polar orbiters are shown. Data appears in AWIPS after it's downlinked from the satellite at Svalbard and then flows through a series of computers in a process that takes about 60 minutes. If you have access to direct broadcast antenna data, as shown in that small image, you can have NUCAPS soundings in AWIPS more quickly, about 30 minutes. NUCAPS soundings are produced using first a regression and then a physical retrieval. The regression step uses coefficients trained from cases that used all sounder and microwave data and ECMWF model output on select days in the past. These past days were used to find coefficients forcing the best statistical relationship between the satellite data and the profiles of temperature and moisture. Best being subject to the constraints of the weather on the test days, of course. That set of static coefficients are used with present-day regressions. Regressions with daily data use all channels, so they capture more vertical structure than in the final physical retrievals that use a subset of sounder, that is CRIS or IASI channels. The regression is done first with all data to produce temperature and moisture profiles, and these data are used to do cloud clearing. More on that in a minute. Then a physical retrieval is done using a subset of 399 of more than 1,300 CRIS channels as shown on this chart. A different subset is used for IASI on MEDOP, of course. In the physical retrieval, the algorithm sequentially solves for temperature, moisture, ozone, and other gases. The first guess for this is climatology. Think about what that means if you're in a regime that deviates significantly from normal. There are 24 channels highlighted in green from which surface temperature is retrieved, 62 channels highlighted in red from which water vapor is retrieved, etc. These channels selected are most sensitive to one gas while being less sensitive to other gases. That is, they have high but not perfect spectral purity. In contrast to the subset of sounder channels shown here, all microwave channels are used in NUCAPS. The ATMS retrieval is the solution if either the cloud clearing fails or if the physical retrieval fails. NUCAPS resolves about 9 to 10 vertical levels of water vapor and about 20 layers of temperature in the entire atmosphere, not just the troposphere. This includes the stratosphere. These charts show the average kernel width function for temperature, and it shows how the effective 1 CRIS spectrum might be spread out in the vertical. There is some geographic variability to the kernels. Cloud clearing is an important part of the NUCAPS algorithm. From the algorithm perspective, uniform clouds are the biggest problem. Each NUCAPS footprint contains 9 CRIS for Suomi-NPP or IASI for MEDOP fields of view. If there is spatial variability to the clouds among those 9 fields of view, NUCAPS will nevertheless produce a good product. If there are uniform clouds across the 50-kilometer scene, then it's more likely to be rejected, even if there aren't a lot of clouds. This shows the 9 fields of regard in CRIS for each NUCAPS sounding. At nadir they're closely spaced, and toward the limb they are more widely spaced. It's not uncommon for sky conditions to vary across the fields of view. I use fields of regard interchangeably with fields of view, you might notice that. The sounder fields of regard do not extend to the edge of the swath. A physical retrieval is used to produce the sounding, minimizing the difference between observations and calculations. If the environment really deviates from normal, the first guess is climatology. The retrieval has a lot of work to do to converge to a solution. If that convergence to a solution doesn't happen, the sounding is still produced, but it's flagged. What is observation minus calculation? The OBS vector is a cloud-cleared radiance spectrum using the subset of CRIS or IASI radiances. The calculated vector is from a radiative transfer model that uses the regression solution trained with the ECMWF in climatology. The final output is mapped to 100 levels that are standard for a radiative transfer model. You'll notice the 100 levels in AWIPS are always the same pressure level surfaces. It's really more levels than are resolved. This slide shows what is available from NUCAPS soundings and what is in AWIPS, which is in the red box. Think of degrees of freedom as something like the layer resolution. That is, there are approximately 6 to 10 layers of temperature resolved in the profile in the troposphere, and 4 to 6 layers of moisture resolved in the troposphere. Do not expect to see very thin layers in NUCAPS soundings. These are tropospheric values versus values for the entire atmosphere that were shown earlier. These degrees of freedom are valid for the physical retrieval that moves around or alters the regression first guess. How do you access NUCAPS sounding in AWIPS? NUCAPS soundings are satellite data. They sit under the Satellite tab. Click on it and then click on NPP Products. Under NPP Products, you'll see NUCAPS sounding availability. Click on it. Doing so will bring up the location of the latest NUCAPS sounding points, which are denoted by green circles. Soundings are available at each of these points. These soundings from 1850 UTC were likely available starting around 20 UTC. Plotting the points on a satellite image, this is the VIIRS 0.64 micrometer visible imagery, is a worthwhile task. It will help you anticipate what the soundings will show. To access the soundings, simply click on a green dot. Here's another example that shows the NUCAPS soundings plotted on top of a VIIRS 0.64 micrometer image. Note again that the NUCAPS sounding data do not extend to the edge of the VIIRS swath. Let's take a look at 3 soundings on this image, one in clear air, one near a cloud edge, and one in deep clouds. The sounding in clear air over North Carolina is smoothly varying, as is typical for vertical profiles from satellites. The sounding near the cloud edge shows marginally more boundary layer moisture. It is likely that one or more of the 9 fields of regard for the sounding are in clear air. The sounding in deep clouds looks non-physical, but sounding properties above the moisture, near the tropopause for example, likely contain useful information. Color-coded dots are new to AWIPS 16-2.1-7. Yellow and red points have failed quality control. Green points have passed quality control. Red points denote soundings for which microwave and infrared retrievals have both failed. Yellow points denote soundings for which the microwave retrieval completed successfully, but the infrared or sounder regression or retrieval failed. Green points are good. This slide shows 4 consecutive passes. North of 40 North, there's an overlap from one pass to the next. But there are regions over the southern U.S., small regions, that are unsampled. Of course, these regions differ from day to day as the orbits shift eastward from one day to the next. There are similar gaps globally. Why do you want to use a satellite sounding when you have numerical weather prediction soundings? Well, sometimes models are wrong, or at least contaminated by convection. Timing issues in models can cause problems. Wouldn't it be better to use an observed NUCAPS sounding in southeast Colorado on this day versus the sounding from the model? NUCAPS soundings were evaluated HWT in 2015. Here are some comments from participants. For our purpose in the HWT, which is severe weather forecasting, the NUCAPS will be most useful for filling the spatial and temporal gaps that exist in observed sounding information and in providing an update to how the thermodynamic environment has changed since the morning soundings. Here we have 2 different feedbacks from 2015 separated by a red line. NUCAPS soundings occur about halfway between the 0Z and 12Z soundings, and they can be used as a benchmark to see how things are changing. On the bottom, there are 2 NUCAPS soundings in different regions, and the different weather in those regions was supported by different NUCAPS parameters. NUCAPS soundings were used to confirm initial analyses of the atmosphere. If you edit the lower part of the sounding, the part that is observed with the least accuracy from the satellite, if you do that to match nearby METARs by altering the temperature and dew point, details on how to do that will be shown shortly. If you do all that, you'll get a better representation of the thermodynamic profile. In this case, a special 18Z sounding is used to compare to modified versus unmodified NUCAPS sounding. The sounding modified to reflect surface METARs agreed with the special sounding. Here's another example over West Texas. After the sounding was edited, its surface-based CAPE was much more in alignment with other estimates. NUCAPS can give clues about the environment ahead of and behind a cold front. There's not a lot of convection with this cold front. Notice the small bump between 850 and 700 millibars ahead of the front. The following slides compare NUCAPS and GFS statistical performance using nearby radiosondes as the baseline, or truth. The comparison on the left is for NUCAPS and GFS temperature biases and standard deviations, and the comparison on the right is for moisture biases and standard deviations. NUCAPS performance is best for moisture in the mid-troposphere, where the bias is closest to zero. Also note that NUCAPS moisture bias is lower than that from GFS in the same part of the profile. This example is for 1 week at the beginning of 2016. This example is for all of October 2015 for Norman, Oklahoma, and it includes 51 soundings that pass quality control. Again, the moisture bias for NUCAPS is smallest in mid-troposphere from 300 to 700 millibars, and that bias is better than GFS. A graphical editor in AWIPS allows you to grab the sounding and move it, either the temperature or the dew point lines. It's common enough to see surface values from METARs that do not match values in nearby NUCAPS soundings. Work is ongoing to make this change automatic, and it may be available by HWT in 2017. In the meantime, however, you can do manual editing. Here's the sounding from Philadelphia from the previous slide. The temperature and dew point do not match METAR observations. To edit, toggle Edit Graph to On. Move the draggable points around to create a sounding that matches surface observations. Be careful, there is no undo button. In this case, the temperature near the surface has been increased to make it more closely match METARs. This in turn changes the LCL, or the equilibrium level. No change has been made to the dew point line, but that could be done too. If you think an inversion is too weak, change it. Are you happy with your changes? Then toggle Edit Graph back to Off, and you have the final result with different thermodynamic variables. Compare the modified sounding to the original. Convection-related parameters such as NUCAPE will have changed. So has the LCL and the EL. This is a more forecast-specific use of the soundings, courtesy of Dan Neatfeld. Will that broken cumulus field on the border of Iowa and Nebraska develop? The GFS is predicting QPF later in the day. Suomi-NPP overflies the central United States around 18 or 19 Z, and this provides timely information on the state of the atmosphere in early afternoon. Here we have 3 different scenes, zooming in from North America to the plains to WFO Omaha. Let's look at the sounding in eastern Nebraska circled in red. This sounding has a surface temperature and dew point close to observations, so we needn't edit the sounding to bring it into accord with observations. The CAPE is small. Would you expect convective development? Late afternoon visible imagery shows that the cumulus field dissipated. A couple days later, Omaha experienced severe weather. This image shows the storm reports, damage, and 2 NUCAPS sounding sites from 1849 UTC on June 3rd. Note also the gradient and dew point in the plotted METARs. The next page shows the NUCAPS sounding for the site just south of the Omaha WFO, the one in the green box. This sounding has been modified so the surface METARs match the sounding values. The surface-based CAPE is a little over 1800. We just looked at the sounding in the box. You'll notice the box is in clouds, but some of the 9 points surrounding that are going to be in clear sky. The sounding point to the south is in a clearer region, and recall that there is a strong dew point gradient over the region. So what will the sounding look like there? Zooming in again, we see the sounding from the cloudy region boxed in green, and also a second sounding point to the south where the skies are clearer and where dew points are warmer. Here's the unmodified NUCAPS sounding from that southern site. Surface-based CAPE is around 700, but the surface temperature and dew point in the sounding do not match the METARs. This is a good sounding to edit. Once the sounding is edited so that its lowest temperature and dew point match the METAR, surface-based CAPE exceeds 3000. This kind of information should influence your interpretation of present conditions. Recall what that point means in the NUCAPS sounding field. NUCAPS soundings are derived from 9 CRIS fields of regard for Suomi-NPP or 9 IASI fields of regard for MEDOP. The point as plotted in AWIPS is the centroid of those 9 points, so information from the sounder is coming from the region surrounding the point. Rather than the point, you should consider the NUCAPS sounding volumetric. That is, it's telling you something about a cylinder of air in the atmosphere. And recall that the region that is sampled, the column or the volume of air, changes in size as you move from nadir out to the edge of the scan. A summary of the training is on this slide. Remember, NUCAPS gives a timely update to 12Z soundings. Use them to diagnose how the atmosphere has changed. You may have to modify the sounding to reflect surface conditions. Statistically, the best information from the NUCAPS sounding is moisture information in the mid-troposphere. This concludes the training on NUCAPS soundings in AWIPS. Thanks for listening.